Hello everyone, welcome to EN4593 Autonomous Systems module. The topic for today is least squares. Here is the outline. First, we will discuss the method of least squares. Next, we will briefly present the broader idea of linear regression. And after that, least squares curve fitting will be discussed. And finally, we will use the method of least squares for the application of accelerometer calibration. The method of least squares is a fundamental topic in linear algebra, and it is often used in data fitting applications. Carl Gauss, who is regarded as one of the greatest mathematicians of all time, is credited for inventing this technique. He actually had used this technique to predict the position of the dwarf planet Ceres, accurate to within half a degree, in 1801 when he was 23 years old. Now, if you can remember, I also mentioned that the Kalman filter was originally derived using the method of least squares by Rudolf Kalman. So I believe you would understand the importance of least squares method, and now let's see what it is. If we consider the scenario where we have observations Bi of some phenomenon at discrete points in time Ti, then we can arrange those in a set of ordered pairs like this. So we have T1, B1, T2, B2, and finally we have Tm, Bm. Okay. So we are interested in finding the equation of a curve y equals ft that closely fits these points in D. So once we do that, we are in a position to make estimations or predictions at points that are in between or beyond these observation points we have, right? In this figure, you can see we have the ordered pairs T1, B1, T2, B2, and T3, B3, and so on. Okay, so we are trying to fit a straight line to these points in D, and here it is given by alpha plus beta t. Okay, now it is totally understandable that we will not be able to come up with a line that nicely go through all these points. In fact, that is not our aim. So there can be different lines we can think of to fit these points based on different criteria. So the question is, what line should we choose? In the method of least squares, the straight line we are interested in is the one that minimizes the sum of the squares of the vertical errors epsilon 1, epsilon 2 up to epsilon m. Okay, so basically we want to find the coefficients alpha and beta in this straight line equation that minimizes those squared errors. So why vertical errors? Well, it would have been better if we considered maybe the perpendicular error towards the straight line, right? So maybe we consider this distance, this one, and this one, and so on. So why aren't we doing that, but considering the vertical errors? Can you think of why? We consider only vertical errors because we are going to assume that only the observations Bi are subject to error or variation, and the time instances are perfectly known. Now, if the Ti's are also subject to variation, then horizontal as well as vertical errors have to be considered, and a more complicated theory known as total least squares have to be used. So we don't want to complicate things too much, and for the purpose of linear estimation, our assumption of errorless time instances would be alright. Okay? Alright. Now since we are dealing with vertical errors, let's also consider the points on the line that correspond to those time instances. Those pairs would be T1 ft1, then T2 ft2, and so on. Okay, so the error epsilon I for each instance would be the magnitude of fti minus bi, right? Fti minus bi, which is equal to the magnitude of alpha plus beta ti minus bi. Got it? Now, the errors can be positive and negative, and in fact, that's why we considered the magnitude of these errors. But on the other hand, it is better if we use the squared errors from a linear algebra perspective. So our objective is to find the values alpha and beta such that the sum of the squared errors is minimal. So I can write it like this. So I get the sum I equals 1 to m, and I'm considering the squared vertical errors, and that would be equal to alpha plus beta ti minus bi squared, and this is to be minimized. Okay. From calculus, we know how to find a minimum value of a given function, right? So we can have two equations, DABA by DABA alpha of the summation of errors which is equal to 2 times alpha plus beta ti minus bi. So this should be equal to 0 at a minimum. And similarly, if we take DABA by DABA beta, and similarly I have alpha plus beta ti minus bi squared. So this is equal to, again, 2 times alpha plus beta ti minus bi times ti. Okay, so this is also equal to 0. Got it? We can rearrange the terms of these equations and obtain the following. So we have the summation times alpha plus the summation of ti times beta, and this would be equal to the summation of bi. So this comes from the first equation, and from the second equation we get the summation of ti times alpha plus the summation of ti squared times beta, which is equal to the summation of ti bi. Okay, so please check carefully and verify what we obtained here is true. Okay, now I want to put the two equations into matrix form. But instead of doing it in the usual way where I have these elements in a matrix, I would rather go for an interesting formation of elements. So I will set A to be all ones in the first column, and we have T1, T2 up to Tm. So this is an m by n matrix, and I will set B to be B1, B2 to Bm. So this is going to be an m by 1 matrix, and X is equal to alpha and beta. So this is n by n, and n is equal to 2 in this case, right? Then the above equation will become A transpose AX equals A transpose B. Okay, now I want you to take few minutes to actually verify that this matrix equation is exactly what we have above. Meanwhile, you must be wondering what it means by AX equals B. So if we write that, we get alpha plus beta T1 equals B1, alpha plus beta T2 equals B2, and finally alpha plus beta Tm equals Bm. Right? Well, a solution to Ax equals B would give a line through all the points, and that is highly unlikely, right? In linear algebra terms, we say that Ax equals B is inconsistent most of the time. A transpose Ax equals A transpose B is known as the associated system of normal equations of Ax equals B. Okay, and it will give us the best solution in least square sense, as we saw before. So from linear algebra, we can prove that there will always be a solution to A transpose Ax equals A transpose B when the rank of A is equal to n. Okay, so I hope you remember what it means by the rank of a matrix. So it tells us the number of linearly independent columns or rows of a matrix, right? So if you look at A, what is the rank of this matrix? Well, it has 2 columns, so the rank should be less than or equal to 2, right? And by looking at the second column, we definitely know that since we have the time instances, they cannot be the same. Therefore, the rank of matrix A would be equal to 2, or n, the number of entries in X. Okay, so the rank of matrix A is equal to n, and that means we have a unique solution to the system of normal equations. And can you find that unique solution? So it's simple, because this is our equation, right? So we know that there will be a unique solution, and from this equation we can easily write that unique solution. X equals A transpose A inverse times A transpose B. Understood? So in the very rare case, if Ax equals B is consistent, so that is when the line goes through all the points, then both these solutions will be the same. Okay. we can elaborate on the answer of X. That is, A transpose A is equal to this guy, right? So this matrix, which is a 2 by 2 matrix in this case, and you know how to find the inverse of a 2 by 2 matrix, right? The diagonal terms would swap and the off diagonal terms would get a negative sign. So we would obtain the summation of ti squared, and here we have m, right? And when the sign changes for the off diagonal terms, we get minus sigma ti, and again the same thing here, and this should be divided by the determinant, which is equal to m times sigma ti squared minus sigma ti, this whole thing squared. Okay, so that is the inverse of A transpose A. And next we have the remaining this part, and that would give us sigma bi and sigma ti bi. Okay, and that is actually this guy here. All right, so we can further simplify this. This term would remain same, and I'll multiply these two matrices to obtain sigma ti squared times sigma bi minus sigma ti times sigma ti bi, and in the second row we have m times sigma ti bi minus sigma ti times sigma bi. Okay, so this is the answer alpha beta that we need, right? So finally we can also find the total sum of squares of the errors, which is given by this equation here, right? So again, that would be actually equal to this guy, right? So alpha plus beta ti minus bi is this, and we can get this square by multiplying the transpose and itself, right? So this is actually equal to ax minus b transpose x minus b. That gives the total sum of squares of the errors in the solution that we have found. Understood? We can do a simple example to reinforce what we learned so far. Let's say that this table gives us the annual sales of a small company in tens of thousands of dollars. Okay, so when we plot it, we can observe there is a linear trend, right? So if I were to predict the company's future sales, I can use least squares method to come up with a straight line that fits these points. Okay. We can identify the corresponding matrices for this problem. So A would be equal to 1, 1, 1, 1, 1, 2, 3, 4. And we have B is equal to 23, 27, 30 and 34, and x is alpha and beta. Okay, so the associated system of normal equations would be A transpose AX equals A transpose B, and from that we would get 4, 10, 10, 30 times alpha and beta, and on the right hand side we would get 114 and 303. So please check these. Okay, so if you work that out, you will find alpha is equal to 19.5 and beta is equal to 3.6. So we get a unique solution, and therefore we get ft equals 19.5 plus 3.6 t. Okay, so that's the straight line that fits these observations or the provided values in least square sense. We can also find the sum of the squares of the errors, and if you work that out, you would get 0.2. All right. Now it is worth mentioning about linear regression and how it is related to our theme. Classical least squares we discussed before comes under the broader topic of linear regression. So in linear regression, we basically express one variable as a linear combination of several variables. Okay, so we have y equals alpha naught plus alpha 1 t1, alpha 2 t2, and alpha n tn plus epsilon. Epsilon is a random function whose values will average out to 0. Okay. For example, let's say a pint of ice cream loses its weight when it is stored at very low temperatures due to various reasons. So these parameters can range from storage temperature, the storage time, humidity, pressure, so on and so forth. Okay. However, we have recognized that temperature and storage time are the primary factors for weight loss, and the remaining factors would average out to 0. Alright, so we are going to describe this system with a function like this, where we have two main factors t1 and t2, and we need to find out alpha naught, alpha 1 and alpha 2. So we approach this linear regression problem the same way we did in least squares, no difference. So we first identify the matrices. So we have A matrix, which is equal to 1, 1, minus 10, 1, 1, minus 5, 1, 1, 0, 1, 2, minus 10, 1, 2, minus 5, 1, 2, 0, 1, 3, minus 10, 1, 3, minus 5, and 1, 3, 0. That's our A matrix, and we have B vector, which is equal to 0.15, 0.18, 0.2, 0.17, 0.19, 0.22, 0.2, 0.23, 0.25. Okay, and here we have three unknowns. So x is equal to, let's say, alpha naught, alpha 1 and alpha 2. Alright, so by employing the same technique, we have the associated normal equations. So that would give us 9 18 minus 45. So please work this out and find these matrices by yourself. And then we have 1842 minus 90 minus 45 minus 90 and 375. So that is A transpose A times alpha naught, alpha 1, alpha 2, and that would be equal to A transpose B, which is 1.79, 3.73 minus 8.2. Alright, so we can solve this and get a unique solution, and from those answers to alpha naught, alpha 1 and alpha 2, we would end up with y equals 0.174 plus 0.025 T1 and 0.005 T2. So that is our least squares answer for this problem. Okay. Now we are ready to have a look at curve fitting using the least squares technique. The curve fitting problem is not much different from the line fitting scenario. Now if you look at this figure, you can see that we want to find a polynomial with a certain degree that fits the given data points in least square sense. Okay. Again, we will be considering the vertical errors, and we want to minimize the sum of the squared errors epsilon 1 to epsilon m. Okay. Just like before, the sum of the squared error is given by ax minus b transpose times ax minus b. Okay. In this case, A is given by this matrix. So you can see a certain pattern here, right? So we have T1 up to Tm, and then T1 squared up to Tm squared, and finally T1 to the power n minus 1 to Tm to the power n minus 1. Okay. Then for B, we would again have B1 until Bm, that vector, just like before. And for the x, which is the unknown, so we can have alpha naught, alpha 1 up to alpha n minus 1. Okay, so again we consider the associated normal equations, and a unique solution which is same as before would exist. So whether it is a straight line or a polynomial of a certain degree that we want to fit the given data points, it is just a matter of correctly identifying the A matrix, and the rest are pretty much same, right? Along with the discussion we are having, there is one interesting piece of information I want you to know. Have you heard of Lagrange interpolation polynomial? So from linear algebra, if we have m number of points where xi are distinct, then there will be a unique polynomial of degree m minus 1 that would pass through all the given points in S. And that polynomial is what is known as the Lagrange interpolation polynomial. Okay. Since we have been told that all those points satisfy this polynomial, we can write m equations like this. So for x1 we have this one, x1 and y1, then x2 and y2 up to xm to ym. Okay. Those m equations can be transformed into an m by m system using matrices, just like this. Okay. And the coefficient matrix is known as Vandermonde matrix. So this Van der Monde matrix is invertible, or we call it as non-singular. Okay, therefore there will be a unique solution to this system. In other words, we can find alpha node through alpha m minus 1 uniquely to find the Lagrange interpolation polynomial. Okay, so you might be wondering, if we have such a polynomial that goes through all the points, then the problem is solved, right? No need of all this least square theory. Well, what do you think? Let's say we have 4 points like this, okay? And according to what we just learned, we could fit a Lagrange polynomial of degree 3 that goes through all these points. So we might end up with something like, let's say, like this, which is the Lagrange interpolation polynomial. But again, when we look at these points, we can also think of a linear trend like this. Okay, so we have this. So what do you select when we have such a problem? And what do we actually want? That is the question. One reason why we don't settle for Lagrange polynomial is generally the observations we make are noisy. So we don't need a curve that exactly goes through those noisy observations, right? So what we actually want to capture is the trend of the observations and not the exact observations themselves. Understood? Another reason is that when we fit an exact curve, there will be many oscillations in the curve. When the number of points we deal with become larger, the oscillations will also become prominent as well. That is something we don't want. As a result, the Lagrange interpolation polynomial is not very useful in making estimations. We can have a quick look at an example for least squares curve fitting. So there is a missile coming from enemy territory and some observations at different intervals were made. We want to know where it is going to hit on the ground. Okay, so the first thing to do in curve fitting is to assume the degree of the polynomial. So let's say we assume a parabola with degree 2. Okay, so function ft would be equal to alpha naught plus alpha 1 t plus alpha 2 t squared. Okay, now the remainder is straightforward. From the data we identify the A matrix and B vector, and we can easily find x, which is the vector with the unknowns, right? So we would have A equal to 1 0 1.25 1.5. So these are coming from the table. 1.75 1 1, and the next column is going to be power of 2 of the first column. So here we get 0 625 0.25 0.5625 and 1. So that is our A matrix, and x would be alpha naught, alpha 1, alpha 2. Okay, and B, again from the table we have 0 0.008 0.015 0.19 and 0.2. Okay. So if you do that right, you would end up with a least square parabola ft equals minus 0.000286 plus 0.03983t minus 0.01943 t square. That's it. So please check this answer. There was nothing new, we just adhere to the same procedure. Okay. Alright, now we are prepared to use least squares technique in a slightly different but more relevant application in autonomous systems. As covered in IMU theory, accelerometers play an important role in attitude estimation, and it is even more important to calibrate an accelerometer to be useful in whatever the application we are going to use it. What does it mean by calibration? So when we use any device such as a sensor or an actuator, we have to be sure whether it functions in the required way. That is, say for example, we have a temperature sensor and we want to know whether the displayed output is accurate or not. We can know that by giving it a standard or known input and observe what it outputs, right? So the process of checking the accuracy of a device by comparison with standard inputs is known as calibration. And not only that, but adjusting the instrument to be aligned with the standard input is also called calibration. So basically, once we know the discrepancy, we can establish a relationship between the output and the input and use that to correct the device. Okay. An accelerometer measures what's known as the proper acceleration. That is the acceleration of the attached body with respect to a free-falling object. So if I ask you what is the accelerometer reading if it is fixed to an object that free falls due to gravity, what would be the answer? Well, it should be 0, right? So we will get a reading AX, AY, AZ. That would be 0, 0, 0. Okay. How about if we fix it on a stationary table? So you will get a plus G on the Z axis, AX, AY, AZ. So that would be 0, 0, plus 1 transform, and the units of G. Okay. So upwards because we are measuring with respect to a free falling body. Okay. Now how can we calibrate the accelerometer sensor? Any thoughts? So we can utilize the known gravitational acceleration, that is both the magnitude, which is nearly equal to 9.81 ms-2, as well as the direction to calibrate our accelerometer. Okay. There are three aspects we need to rectify when calibrating an accelerometer sensor. When we attach the accelerometer to the object of interest, which can be a quadcopter, a ground mobile robot, or even a self-driving car, there will be a misalignment between the accelerometer axes and the object body axes. Okay, so that's one thing we need to correct, the misalignment. Then there is sensitivity or the scale factor. Finally, there can be 0G level, or we call it as the offset. So these are the three factors that we have to rectify. Okay. Now we can put this information in matrix form. So first what we are going to do is we will remove the offset. Okay, so let's say we take the sensor reading and remove the X offset, and we remove the Y offset, and we remove the Z offset. So S is sensor and OS is offset. Okay, so after we remove the offset, we need to scale it. So that can be done using a 3x3 matrix. So we can have alpha, beta, gamma as our scaling factors. Okay, let me write this as the offset, and this guy is for scaling. Take a moment to understand how it gets scaled by this 3x3 matrix once we remove the offset. Okay, and finally, to correct the misalignment, we will use a rotation matrix. So this is the object to sensor rotation misalign. So it will align with the body frame, right? So once we do that, then we will get the readings in the body frame. AY object, AZ object. Okay, so let me repeat that. So we get the sensor reading, right? So there can be a 0G level or an offset. So we first remove that, right? And after that, we can scale the 3 readings by this matrix. And finally, we will align it to the object frame. So we started with the sensor frame and we want to align it to the object frame using this matrix, right? So that we get all the accelerometer readings in X, Y, Z directions in the object frame. Now, if we take the first 2 matrices, the 3x3 matrices, we can multiply them and we will get another 3x3 matrix, right? So let's call it, the elements, let's call the elements as C11, C for actually calibration, okay, C12 and C13, C21, C22, C23, C31, C32 and C33, and we can have the sensor reading like this. Sorry, that should be S, Z, okay. And now this product, this matrix, when multiplied with this offset part, we get another 3x1 vector, right? So I will put it here for the time being. C14, C24 and C34. Okay, so here OBJ is object. So finally we get this form. Okay, we can do a nice improvisation and do something interesting if we use homogeneous coordinates. So in homogeneous coordinates, we append a 1 to the row sensor reading vector to make it 4 by 1, right? So we have the row sensor reading and we append a 1 to make it 4 by 1, right? And when we do that, the previous 3 by 3 matrix will be reshaped, and we are going to add another column that comes from the offset. So we have the original one here, 1 1 1 2 1 3 3 1 3 2 and 3 3, and now we have that offset part in this column. So with the homogeneous coordinates and with this one, you can understand that these three guys will be added, just like what we had in the previous slide. Okay, so this is in homogeneous coordinates, and this is our row sensor reading. So this is our calibration matrix, and please note that now it has become 3 by 4. Okay, so this 3 by 4 calibration matrix will transform the row accelerometer readings to the corrected output. Understood? So how do we find this calibration matrix? And that is where the least squares method comes in. It is just a matter of putting our system into the form A transpose AX equals A transpose B. Okay, so the parameters that we need to find is inside this X, and we want to identify the matrices A and B, so they will come from the input and the output. Okay, the least square solution should give us the entries in the calibration matrix C11, C12 up to C34, and that should be our plan. All right, so how can we do that? Any thoughts? We are going to keep the accelerometer attached object in several known configurations, and we will record the measurements. And this table shows some known configurations we can use. So when the object's z-axis is downwards, we want the accelerometer to give -g in its z-axis reading after calibration. Similarly, when the object's x-axis is upwards, we want the accelerometer to give +g in its x-axis reading after calibration, and so on. So it would be the calibration matrix's duty to do that transformation on the row sensor readings. Okay. In order to represent this system in the way we studied, we may need to do some slight modifications. First, I will transpose the whole equation. So left transpose and right transpose, and we will obtain AX object, AY object and AZ object. So that's the transpose of the left one. So that would be equal to A6 AY AZ and a 1. Next, we have the transpose of the calibration matrix, right? So we would get C11, C12, C13, C14, our first column, then C21, C22, 23, and C24, and finally C31, C32, C33, C34. So this is a 4 by 3 matrix. Okay. Now I will start collecting row sensor readings for those configurations previously shown. So it works like this. Keep the object in known configuration 1, collect say 100 samples. So I can have a matrix like this, and I will collect 100 samples in that known configuration, right? Then change the object to known configuration 2. Again, say we collect another 100 samples. And so on, okay? Right. Now on the left-hand side, we would have the expected readings for all these known configurations. So let's say for the first one we have 0, 0, minus 1, 100 times, something like that, okay? Then we would have 0, 0, plus 1, and finally we can have plus 1, 0, 0. Alright, so these are the expected, and these are row readings. Right, so this is going to be n by 3, where n is the number of observations, and this is n by 4. Okay, now if we take the first column of this left matrix, so I'm going to take this one, and let's call it as B1 vector. Okay, B1. Therefore, we can write this combination as B1 equals A times X1. So here we have X1, and this whole thing is going to be our A matrix, right? So B1 would be equal to A times X1. Understood? Now if we take the second column of this left matrix, we can call it as B2 vector. Therefore, we can write this combination as B2 equals A times X2, where X2 is this one. Okay. And finally, if we take the third column of this left matrix, let's call it as B3 vector. So this combination would be B3 equals A times X3, where X3 is this one. Okay, so we have three systems: B1 equals A X1, B2 equals A X2, and B3 equals A X3. Actually, we can solve these three systems separately in least square sense using the associated normal equations. But we can improvise again and do better than that. That is, we can combine all those B vectors together to form a capital B matrix. So this is the capital B matrix. And combine all the X vectors together to form a capital X matrix. So all this would become the capital X matrix, so that our equation becomes capital B equals capital A times capital X. Okay. There will be no difference to the technique we learned, even though we have matrices instead of vectors now. Therefore, we can have an associated normal equations as before, which is given by A transpose B equals A transpose AX. And the solution would preserve the same nature of our original solution in least squares. So we have X equals A transpose A inverse times A transpose B. In fact, this X is our calibration matrix, right? Or I would say the transpose of the original calibration matrix. So in this formation, here we have the raw sensor readings, and on the left we have the calibrated output. Okay, so now we can use this calibration matrix to obtain accurate measurements in least square sense given any raw sensor reading. With that, we have come to the end of this lecture. Let me summarize what we learned. First, we introduced the method of least squares, and from linear algebra we understood that there will always be a unique solution if the rank of matrix A is equal to n, which is the number of unknowns. Next, we extended the concept for curve fitting. We understood that even though there is a polynomial known as Lagrange interpolation polynomial that can fit exactly all the points, that polynomial would not serve the purpose of estimation. Finally, we used the method of least squares in a more relevant accelerometer calibration application. Thank you.